All right, good morning, everybody. How's it going? Hey, guys. So, my name's Tim Dodd, but I'm better known as the Everyday Astronaut. I teach rocket science on YouTube, and, rockets are awesome, right? I mean, I know this is an EV convention, but I think there's still a lot of crossover, just an exciting technology, and in my opinion, there's really almost nothing more exciting than rockets. You know, they're pretty cool. But there's one problem, and there's no getting around the fact that, quite frankly, rockets do pollute a lot. And we're going to talk about that today. We're going to talk about just how much do rockets pollute. Because there's no getting around it. What comes out of the back, it's certainly something. And it's going without me because I don't know how to run a PDF. So here's what's interesting. The good news is, I'm going to start off, this is going to be a roller coaster of emotions. Actually, I have a lot of precursors to this. This is going to be a roller coaster because it's going to be like, this is great, but it's not. Oh, but this is not a big deal, but it is a big deal. So just get ready, prepare your emotions, settle your heart, free your mind, or whatever Ben Solon says about data, mindful, something. Sure, do that, get ready. But here's the biggest disclaimer. I am not a scientist. I am not good at this stuff yet. I'm still just learning myself on all of this. So there's a giant asterisk, and I always say that wrong. It's probably asterisk or I don't know. I'm a giant one of those. If you see something in this presentation, if you are, please, if someone in here is a scientist, if you're a chemist, if you do anything with actual, the EPA, and you actually know what you're talking about, please come talk to me, because I'm still compiling this stuff. I'm still learning it myself. This has been over 3 or 4 months for me to be able to put this all together. And I'm working on it for a video. Once that video goes online, I don't want it to be wrong. So this is the time now to catch it before it becomes a thing. So let's start off with this. Boom! See all this? There's a lot of stuff going on right there. That's a rocket called the Falcon Heavy. I don't know if you've heard of it. It's really cool. This is a picture I took. The camera was 1,000 feet away, 333 meters, whatever, away from it at Launch Pad 39 in Kennedy Space Center on February 6, 2018. And you see this giant cloud of what looks like smoke. But here's the first bit of good news. That's water. That giant white cloud is actually straight up water vapor. And you'll notice as most rockets climb, a lot of them, as they climb and leave the launch pad, you'll notice it switches to a relatively clear exhaust trail. That beyond the flames, because the flames are awesome, beyond that, there's literally there's not much exhaust. It's just kind of clear. Well, mostly. There's some rockets that still have a giant cloud that follows it in the air, and we'll talk about that later. We'll explain why, how, what, when, all the things. So the reason for this giant cloud is actually because of this water tower. That water tower holds over 1 million liters of water, 300,000 gallons, for those of us metrically impaired, and it's a water deluge system. So it pours literally, you can actually see the rainbirds here in the bottom. These towers, those are all around the launch pad. They soak the launch pad in water, thereby absorbing energy, cutting down on noise, cutting down on vibrations and all the acoustic energy that can actually not only rip apart the launch pad, but also the rocket itself. So they pour all this water on, and most of it evaporates into steam, therefore absorbing a lot of energy, and that's the giant cloud we see as it takes off. So now we need to, what can actually come out of the flamey end of a rocket? This is the list of really most of it. There's lots of other small trace gases, but that's advanced chemistry stuff. I'm not that smart. So we're mostly these are the main suspects here. There's CO2, water vapor, carbon soot, carbon monoxide, nitrous oxides, chlorine, alumina, and sulfuric compounds. Okay, well, sure. So out of those, what are considered pollutants, according to the this is the United States' Environmental Protection Agency, or EPA, nitrogen oxides, sulfur oxides, and carbon monoxides are pollutants. Ozone-depleting substances, you may remember these, CFCs, things that we started really heavily regulating in, I believe, 1996. Things that can deplete the ozone or the ozone layer, although it's not really in a layer, and there's no holes getting punched in it per se, but these are things that can actually deplete that, chlorine and alumina. Out of the list of things that can come out of rockets, those are ozone-depleting compounds. Greenhouse gases, not all gases, because soot is not a gas, it's carbon. There's CO2, there's nitrogen oxide, soot, and water vapor are considered powerful greenhouse, I'll make up a new term, greenhouse effectors, sure. We're all familiar with those, and hopefully, I think in this room, I'm safe to say, like, you all understand that that's a thing. Like, oh, greenhouse gases is just like, it's a thing that, absorbs radiation and creates things to heat up. When I put this on YouTube, I'm really nervous to even say the word greenhouse gas, because people will be like, oh, we got you, we knew it. You're a liberal or something. Like, wait, no, it's just, that's what it is. It's a greenhouse gas. Like, that's a definition of it. So, sorry, that's my rant for the day. Chlorine is a hazardous air pollutant. Don't breathe it. Sulfuric compound, also gross. Don't stand in acid rain. I shouldn't have to explain that. Most common rocket fuels, though, are RP1 or Kerolox, hydrogen, otherwise known as Hydrolox. There's methane, Methalox, solid rocket boosters, or solid rocket fuels, SRBs, or you might also hear them as SRMs, solid rocket motors. And there's hypergolic fuels, too. Solid rocket boosters. You'll see on the left side of the space shuttle there, the giant white 45-meter tall, 3.7 meter wide solid rocket boosters. These are made out of ammonium. I still have no idea how to say these. Ammonium perchlorate, salt of chloric acid, ammonium powder, polybutadiene something, and acrylonitrile B-band. I don't know. You can read. So that's what's coming out, or that's what makes up those giant solid white boosters, or those are the most common ingredients. There are some tweaks to those. So that means what actually comes out of solid rocket boosters, the emissions are aluminum oxide, soot, CO2, hydrogen chloride, nitrogen, hydrogen, and a few other trace gases. Not great. A lot of those things are pretty nasty. But on the other end of the space shuttle, on the right, you can see those three little, those little like triangle things. Those are actually mock diamonds coming out of the RS-25 space shuttle main engines. All that comes out of that, because it's hydrogen, is water. When you mix hydrogen and oxygen, you get water. So the space shuttle orbiter itself and the giant orange fuel tank, the only byproduct of that was water vapor. Beautiful. On the other hand, then a really common rocket fuel is RP1 or Kerolox, and this is common on a lot of launch vehicles. Falcon 9, Falcon Heavy. We'll get to that actually in a second. We'll talk about which vehicles. But what comes out of the flaming end on these is CO2, water vapor, nitrogen oxides, carbon soot, carbon dioxide, and sulfur compounds. Then there's hypergolic fuel emissions. Hypergolic fuels are those that wonderfully, when they, depending on how you look at it, when they touch, they go boom. And that can be a very good thing, because you don't have to have an ignition source. So maybe you've heard of hydrazine is a very common fuel for the propellant, and then they use an oxidizer, and when the two things touch, it just instantly lights up. So you'll see this used on like reaction control systems or little gas thrusters, because they can do precise movements and just go, and like just these really quick little bursts. But it's also sometimes used very commonly, for instance, on intercontinental ballistic missiles, because hypergolic fuels are very happy being stored for years and years and years at room temperature. You just that's why they would sit in silos, fueled up, ready to go. You hit a button, and that thing's launching. So don't be anywhere near it. The worst part about hypergolic fuels is actually breathing them in as a fuel state, like as the vapor of the fuel. You likely won't live to tell about it. But when you burn it, it becomes CO2, water vapor, soot, and nitrous oxide. So it's almost better to burn the hypergolic fuels than it is to come in contact. Handling hypergolics and fueling up hypergolic fuels is very hazardous, and you have to wear like a full hazmat suit and stuff like that. The new kid on the block, methane, no rocket has ever made it to orbit fueled entirely by methane or Methalox, or even like a boost stage. So this is actually, Star Hopper, pretty popular now in pop culture. It was pretty cool because it's really about the most work that's been done using a methane-powered rocket for now. But a lot of new rockets are coming on the market that are going to be powered by methane. So that's kind of the new kid on the block. and is kind of a Goldilocks. It has CO2, but it also, the other byproduct is just water vapor. So it's kind of like the mixture between RP1 and hydrogen. So now you'll notice all these vehicles. I chose a smorgasbord here of vehicles. All of them are capable of carrying people. You'll see why we're going to go into this. But so these are kind of a list, and all of these rockets also, we represent all the major fuels we just talked about by studying these rockets. So there's the Titan II, the Soyuz, I'm going left to right, like we do here. The Atlas N-22 with a Starliner on top, the Falcon 9 rocket with a Dragon capsule on top, the Space Shuttle, as we mentioned earlier, then the upcoming SLS rocket, and SpaceX's Starship. Yes, this is an older picture of Starship, but it's so beautiful it had to be in here. So, this is a big old chart. Charts are pretty and cool, but they're very intimidating, so just look at it and enjoy it. I don't know. There's a lot of stuff that comes out of rockets. The dashes don't necessarily mean that nothing, like there's none per se. It's more just like very trace. So actually, almost all of the vehicles have some sulfur-containing compounds, but that's mainly a byproduct of the hypergolic fuels, which is what you can see here. So you can really tell just looking at, the elements that come out of it or the emissions, what kind of fuel it is. But you'll notice one thing. There's one really, 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 really big number here, and it's this. 2,683 metric tons of CO2 will come out of a fully fueled Starship, full stack orbital Starship. We'll get to this, though. Don't worry. I'm telling you, this is going to be a roller coaster here. But seeing these numbers isn't everything, right? Because rockets have to do work. So this is their tons of payload to low Earth orbit. So now you can see already, you can see where I'm going with this because, Starship pollutes a ton, but it also does a ton of work. So now we can see the ton of CO2 per ton of kilogram, per kilogram to LEO. So basically, to get the best you can do is really the SLS. Well, actually, no, Delta IV Heavy. Sorry, the best you can do is Delta IV Heavy because that thing does not produce any CO2. If we're looking at CO2 as our benchmark for being like, let's stop that. Delta IV Heavy is amazing. It runs purely on hydrogen. No solid rocket boosters. It's just 3 cores that are all Hydrolox powered. There's small trace bits of carbon because it uses an ablative nozzle that kind of like rains a little bit of carbon, but it's nothing compared to any other vehicle. So if you want a clean ride to space, Delta IV Heavy, that's great. Full hydrogen, awesome. But now, you actually start to look like SLS, even though it has those giant solid rocket boosters, because it's core stage. Those solid rocket boosters only fire for like 2 minutes. So even though they're nasty and bad and gross, they get ditched pretty quickly. And so the SLS is a pretty efficient way as far as CO2 if you ignore the nasty solid rocket boosters, because its core stage is hydrogen. But Starship Starship and Super Heavy would be like the full orbital version. It's not that bad compared to even the Falcon 9. And notice, though, the Falcon 9 here, tons to LEO, I did quote reusable. We almost never see an expendable Falcon 9 anymore. SpaceX is famous for landing their boosters and now reusing them. When you do that, you do cut the payload capacity in about half. So that number could be, instead of 14 tons to LEO, it could be 28 if they threw it away. But you can guess that that's not also the most renewable source of anything to throw a rocket away. More on that in a second. So that number would change. If this is 28, that would be, 16 and a half. So, yeah, I don't know. Okay, let's keep going. So now we can get something interesting because I used only crewed vehicles. So for now, maybe in the video I'll break this down a little bit more. But I thought it'd be fun to compare. If you're a passenger and you're going somewhere to your destination, how many tons of CO2 are you going to produce when you do that? So, before we get into those numbers, because you might have noticed there's some airplanes on there, some jetliners. There's a 737 and a 747. CO2 and water vapor in the upper atmosphere is really bad. And I can't find a number. If you have a model for me that I can get an explicit number on vehicles emitting large amounts of CO2 and water vapor in the upper atmosphere, please come talk to me, because I can't find it anywhere. And I've tried running models, and I've hired people to like literally try to give me an estimate. So I'm going to say worst case scenario is probably, we'll say it's 100 times worse to have CO2 and water vapor in the upper atmosphere than it is down here in the lower atmosphere. Because in the lower atmosphere, it cycles through, water vapor will cycle as rain. You've all heard of that. And CO2 can get, eventually does come out of the atmosphere just slowly. And yeah. So in the upper atmosphere, it has a lot more time to act as a greenhouse gas. So I don't know how much worse, but just keep that in the back of your head that rockets are different than airplanes because airplanes fly in the atmosphere. Rockets spend a lot of time emitting in the upper atmosphere. So here we go. Passengers, Falcon 9. Notice it says 4. You'll be like, but Tim, the Dragon capsule can carry 7. Mark my word, I don't think we'll ever see more than 4. NASA will not ever fly more than 4. So it won't fly 7, I don't think. If it did, that number would change, but really we'll see 4 at the most. So tons of CO2 per passenger there, 116.75 tons of CO2 to get to low Earth orbit on a Falcon 9. Notice the destination is going to be different because obviously I'm kind of going with your end destination, and getting to orbit is significantly different than going to like Chicago, Those are very different places. But Starship's super heavy. If you're going to orbit, you can put about 100 passengers on there. They can actually take 100 passengers to the moon, 100 passengers to Mars if you refuel the vehicle. But to actually just go to low Earth orbit, say you're going to a space hotel, you could comfortably fit 100 people on there, no problem. And in which case, the tons of CO2 per passenger is 26.83 tons of CO2 per passenger. But SpaceX is not just going to space with Starship. They're planning on maybe doing point-to-point transportation, like replacing jetliners, and you could go anywhere around the world in 45 minutes. Like literally anywhere. The furthest you'd ever have to travel because of orbital mechanics is about 45, 50 minutes away. Pretty awesome. And interestingly, the Starship has 1,000 cubic meters of payload volume. That's more than a 747. So 747 has, I think it's like 780 or 800 cubic meters of pressurized volume. Starship has more than that. So I said, I don't know. I said, you could probably comfortably put 400 people in there. I'm being very conservative. If a 747 can do 416 with less pressurized volume for a 10-hour trip, I figure 400 people will be happy for a 50-minute trip. Again, being conservative. So therefore, a ton of CO2 per passenger actually on Starship is 1.79. Not that far off from a fully, there's one more asterisk. Boop. These guys here, something interesting, you would never really run an airplane fully out of fuel. So this is their worst case scenario. Like if you drained it completely of fuel, don't recommend that. But long haul, that is basically your worst case scenario. It would be 1.45 tons, but the Boeing 737 is very efficient at 0.67, so it'll be a long time before we catch up to that. But here's something interesting. Context on all this. The number of commercial flights per year in 2018, 37,800,000 commercial flights. That's a lot. The number of orbital launches in 2018, 114. There's 331,579 times more commercial flights than rocket launches. In other words, total emissions from commercial flights in 2018, 918 million tons of CO2. Total emissions from rocket launches in 2018, 22,780 tons. In other words, you could fly 40,300 times more rockets per year to equal the CO2 output of the commercial airline industry. So there's a long ways to go. In other words, you could launch 4,594,200 orbital rocket launches, and that's assuming it's the same as our 2018 standards. We're seeing trends towards cleaner, methane. We're ditching solid rocket boosters more and more. At the same time, China, India are both launching more and more, and they're still using hypergolics. They're still using solid rocket boosters. So it might balance out for a little while, where we'll still see kind of 2018 is probably a pretty reasonable benchmark of a year. But that still means you can launch 12,586 rockets a day to equal the airline industry. That's a lot of rockets. So to make that, earlier we saw that Starship was kind of the worst case scenario for CO2 output, right? You could launch 937 fully loaded, super heavy launches, like full-blown Starship super heavy, or 3,512 Starship only. So if you're doing those point-to-point transportations per day, that's still going to be equal to the airline industry. So if this point-to-point thing happens, we can launch quite frequently before we match the CO2 of the airline industry. And the cool thing about this is, obviously, that would likely decrease some of the flights, if we're doing point-to-point. So I'm not really going to draw conclusions, but this is just the number of what it would take to really equal that. But remember, it is taking, see, here's that roller coaster I was talking about. Good news, bad news. But remember, CO2 and water vapor in the upper atmosphere. Again, I don't know how much worse. We'll say 100 times worse. That still means you could do 10 orbital Starship flights a day, which is obscene, or 35 point-to-point Starships. So you could do a third of all the rocket launches in a year, basically in a day, with Starship only point-to-point, and it would still just match the commercial airline industry. So that's not quite as cherry, but still, I mean, considering we launched 114 times in 2018, and that was a high for 30 years, a 30-year high of rocket launches, we have a long way to go. This year, 2020, we'll likely see a lot more. We'll probably break some records again. We'll likely see almost twice as many launches this year as 2018. So keep those in mind, that those numbers are going up, but we have a long way to go. And the big thing is, the commercial airline industry, I've been using them as a benchmark, is only 2.4% of global CO2 emissions. They're not even a big player. I'm using them as like the benchmark here, saying we'll have to get this far just to catch up to them, yada, 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 doobie, da. Really, it's only 2.4% of global emissions come from the airline industry. So current CO2 outputs of rockets currently is 0.00059% of global CO2 emissions. In other words, we have a lot bigger fish to fry. So what can you do to actually make rockets more sustainable? There's two big things. Number one, new fuel. Start using hydrogen and methane more often. Methane, although when methane is released into the atmosphere, it's a really powerful greenhouse gas. But again, when you burn it, it becomes water vapor and CO2. It's less powerful as a greenhouse gas in that form. And importantly, methane can actually be remanufactured. You can pull, using the Spadre process it's called, you can actually pull CO2 out of the atmosphere. You can use electrolysis to create hydrogen and oxygen, and you can actually recreate your rocket fuel by pulling it straight from the air. So if you have a renewable energy source, say solar, wind, et cetera, you can just continually refuel your rocket for free, basically, and be carbon neutral. That's something the airline industry, without any kind of advancement in fuels, that's something the airline industry can't currently do. So keep that in mind, that it actually could be almost carbon neutral to be flying, especially if you're using purely hydrogen, which hydrogen is very hard to work with. It's a pesky, small, undense molecule that it wants to escape out every crevice. You need to keep it near absolute zero temperature, so it has to be extremely cold, so it tends to bleed off very quickly. It's very hard to deal with. Methane is a lot easier in that aspect, so that's why we're starting to see this new trend of people using methane, because it's a Goldilocks. It's right in between RP1, which is a lot easier to work with yet, and it's a lot easier to work with than hydrogen. So that's one of the things. The other big thing that we can do to make rockets more sustainable is stop throwing them away. Right? I mean, duh. Stop, because when you actually look into it, I guarantee you, and I'm working on these numbers too for the video, making a rocket, the CO2 output of producing and manufacturing a rocket, likely is orders of magnitude worse than flying it. There's manufacturing, even steel. Steel is about 8% of global CO2 emissions, just manufacturing steel, mining, blah, 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 blah. By the time you actually get to the steel industry is about 8% of global CO2 emissions. So therefore, if you can start reusing your rockets and not having to make new ones, guess what? That's a huge leap forward in sustainability. Duh. And luckily, that's definitely the big push right now. Again, SpaceX has been the the big push for that, as they've been landing and reusing rockets. They're coming up on, I don't remember if they've now launched a Block 5 Falcon 9 5 times, the same one 5 times, or if it's just been 4 is still the record. I think, I don't remember right now off the top of my head, but yeah, so they're starting to refly rockets over and over. Therefore, you kind of amortize that manufacturing cost, that CO2 throughout multiple launches, So if you only get 10 flights out of it, that's still an order of magnitude better than throwing it in the ocean. So those are the two kind of big things you can do. And when I said we have a lot bigger fish to fry, in the background you notice a leaf blower. Ooh, those pesky leaf blowers. CO2, not necessarily CO2, but non-organic hydrocarbon compounds of a 2-stroke blower, leaf blower. 30 minutes of yard work is equal to driving 2,000 kilometers in a Ford F-150 SVT Raptor. So if we want to talk about things that should probably change, stop using 2 strokes. And that's an easy replacement. EV world, I mean, come on. Like, throw a battery pack on that thing and you run it for a couple hours and recharge, swap batteries, no big deal. That's easy. So if we're worried about global CO2 emissions, I'm not going to focus on the 0.00058% or whatever of global CO2 emissions. I'll look for things that are really easy to change, that are being used constantly. And maybe that's my bias of like, I want to see more rockets launch. I want to go to space more. But at the same time, like, really, I mean, if we're going to focus on something, let's focus on something that everyone uses and that doesn't benefit humanity in scientific exploration and scientific discoveries, because it's such a small, minute. And not to say that we can just leave it like unbridled and be like, oh, they're fine, we don't have to worry about it. Like, let's keep them in check. But until it even gets to 1%, like, I think we can give that a pass, because there's so many other industries that pollute substantially worse than that. So that's how much pollution do rockets create, basically. That is this is my truncated version for you guys. Like I said, this will be an upcoming video. It'll be a little more in depth, because you guys know I like to go real deep into these numbers and really deep on research. So stand by. If you don't subscribe to me on YouTube, get out. There's 2 doors. So no, but that'll be upcoming. You'll see a more polished version of what I just said on an upcoming YouTube video. I have the script done. I have what I think is the research done. I'm still getting feedback from. I've hired researchers on this stuff now, because I want it to be right. I don't want to be the YouTuber that's just like, this is good enough. Because it's the posterity of a YouTube video. It's out there for years. I don't want to be spreading misinformation. So that's why you guys are here, to tell me what I did wrong. So, questions. Starting, I saw your hand up first, actually. So, yes.
I was just wondering what you think the likelihood of point-to-point Starship transport actually happening, given the extreme noise caused from both liftoff and reentry sonic booms.
Very, very, very good question. I think it's feasible. It can make sense, but it won't be this, like, it will not replace airplanes. It won't be, especially inland. It could replace airplanes for, say, cross-Pacific, cross-Atlantic trips. If you're going New York to London, well, even that, like, you'll go from, I don't know, like, 5 hours to 20 minutes? Like, I don't know. Maybe that's not a huge one, but there's a couple trips where it would be feasible. You'll still have to ferry people out to the launch pad and landing pad will be at least 15 miles away. So we're talking so unless there's like a hyperloop or something, or some quick form of transportation to get you to the pad, it really, it won't happen unless something like that also happens. So more like going hemisphere to hemisphere, and then from there you spoke out. Yes, exactly. So hemisphere to hemisphere, longer, the ones that really matter, 6-8 hour plus airplane trips. And, you just have a couple of these. These will be high paying, these will be $5,000, $10,000, $20,000 trips probably. But they'll get you, you can get to Australia from like right here in, 35 minutes, as opposed to, 13 hours, That'd be awesome. That'd be great. But yeah, again, you won't be doing it inland for those exact reasons. Noise pollution, the sonic booms on reentry are crazy. ask anyone who lived in like Titusville or even Orlando when the space shuttle came back in, boom, boom, like it would like wake you up in the middle of the night, obviously. So if we're doing that regularly, it's got to be, away from populated areas, which, yeah. So there will be cases for that. But I do think it's possible.
Hey, Tim, what technology do you see coming in the future to pull carbon dioxide and other greenhouse gases out from the upper atmosphere to reuse in rockets? Because that's obviously, like you said, the bigger deal than just pulling out the CO2 at the surface.
Mm-hmm. I don't know of any technology that'd be able to do that easily. Because the problem is, it's very high up. You can't just have something like, for instance, a weather balloon can't go where there's not really an atmosphere. And we're talking about the very, very, very upper stratosphere where a balloon won't reach. You can't really take something up there unless it itself is flying. So I can't really imagine a technology readily available that would produce, be able to pull down. Because the problem is it's up very high. It's very light trace gases that can stick up there for a long time. And this is where I'm talking a little bit out my rear end, so I might not be exactly correct on why it stays up there. But I think the alternative will be trying to mitigate through, try to kind of almost like tax or, have other ways of carbon capture that are, if it's say 100 times worse, we'll do 100 trees or, mitigating it on the ground to make up for that. Because it just simply stays up there so long and we can't really get to it until it starts to basically deorbit itself in a sense. So I don't really know, I don't know of anything. But maybe someone out there is smart enough to have an idea for that. So, yeah. I saw right down here.
Thanks, Tim.
Yeah.
First of all, this is a comment section thing, so I'm hoping you don't hit in the comments. What about the total life cycle? The transport from Hawthorne to McGregor, all the testing that goes on. So for every launch, there's how many times does a rocket get tested?
Right.
So that'd be 2, 3, 4 times. So that would be the first thing. Mystery, out there, getting the fairing, the gasoline, the diesel fumes, all that stuff. So that's probably hard to calculate, but someone will hit you with it. I didn't want you to get it first, Just so you know, somebody's going to be down, control.
Yeah. No, that's so. Just in case you couldn't hear, you're exactly right. That, and I have been working on some of the manufacturing numbers. I also I did have a slide actually originally that was going to take into account the static fires of rockets too, because it's basically a rocket launch. Although they're starting to cut back on that. They're getting so much data. They're getting so comfortable with their boosters that SpaceX in particular is starting to just cut down. They're not doing full duration stuff anymore. So right there, I'll try to add that up, and I'll maybe even just say I'll come up with some number, and I could try to find out how. I know that the environmental impact of even the recovery vessels and things like that, the tugboats, have to be accounted for Cape Canaveral and for SpaceX and the recovery efforts. Because SpaceX is actually trying to reuse as much of their rockets as possible, but in doing so, they're literally using diesel-powered tugboats and these fast boats that go out there and they catch even their nose cone, their fairings. And they're trying to reuse those, which is great. But in doing so, they're likely emitting a large percentage of the launch's CO2 just in that process too. So you're right. I definitely should make sure I at least give it a crack. Yeah, and try to break it down. I was like, okay, well, here's something else to consider, because there's a lot of considerations. There's so many considerations in this stuff. Yeah, right next to it. Yeah.
I think you're ignoring. And I think you know that you are, reaction engines and the Sabre engine and Skylon, because that would do single stage to orbit, do point to point, just using hydrogen.
Yeah, you're right. And I actually wasn't ignoring it. I'm glad that you reminded me. The Sabre engine is a hybrid rocket engine that can basically perform like a jet engine where there's oxygen, pulling and extracting its oxygen from the atmosphere. Therefore, you're not lugging around your oxygen with you. And then once it gets to that point where that's no longer feasible, and certain Mach numbers, and boom, it turns itself into a rocket engine, which is really cool. And they've made really good progress, especially recently. Their pre-cooler performed a test where it has to take incoming air and shift it into from a really hot phase of oxygen and shift it into liquid oxygen, I believe, within like milliseconds. Are you on the project, or are you?
I'm not on it, but it seems to me that it is the. Sorry, I'm not on the project, but I'm a Brit, so I pay attention. But it does seem that they are breaking barriers, as it were. Their technology, with, as you say, the supercooler, So 1,000 degrees down to minus whatever,
Yep.
20th of a second. And that's also going to go on to, presumably, onto normal jets as well. So it's a technology, that supercooler, that is going to contribute to sustainability.
Right.
And could do single stage to orbit on a daily basis,
Right.
just like a jetliner.
Yeah, yeah, and thank you for reminding me. This is why I'm presenting here too, because I want feedback like that. So that's a good point, that there are other technologies, and I'll make sure and bring that up, and like, what can we do? Sabre engine is definitely a very, very sustainable, or a help for sustaining, especially rockets and fast hypersonic transport. Thank you. Let's go ahead. I saw you for a while, and then there was another one after that. Is that okay? Yeah, we got time for two more. So you, and then, yeah.
All right, thank you. For your comparison chart, I would be interested to see the other players that are upcoming, Blue Origin and Rocket Lab, right? Mm-hmm. The Electron, your friends.
Mm-hmm. Yeah, that chart could be a lot bigger. Yeah, and the cool thing is, I have all the numbers, and I stumbled upon this academic paper that was published in 2014, and I labeled it in my research the document that solved everything, because it gave us a baseline for all the rockets. So they basically did a lot of the things that I was trying to do, which is figure out what exactly comes out of every engine, and they had it for a lot of really common launchers. And we had developed our own, like we had literally just broken down the chemistry. I, again, had hired a research assistant to like literally, and I was like so nervous, what if we're way off? You know, because we're starting from scratch, we're probably forgetting something. What if we're way off? And then we found this document, and we're like, we were like 2%. We were really close. So that was reassuring that then our calculations can be used to figure out Starship. Our calculations can be used to figure out SLS and other things that were missing from that document. So I actually have all those numbers, literally for basically every rocket. So I can just populate that chart up and make it really crazy. So, yeah. And then in the very back there.
Hey, Tim. Thanks for doing this. Appreciate it.
Yeah.
I'm a big fan of space stuff, but really the presentation, doesn't it ignore the fact that this is additive? You mentioned it as a percentage of global CO2 emissions. But the issue is that every rocket launch is being added on to every other rocket launch. And as more and more countries get into space, don't we just compound the problem? You're not subtracting from the other emissions that are already out there.
Right. No, absolutely. Like all CO2 emissions, it's additive, you know, and the point is at 0.00058% of total global additive emissions, it's still just not even, you know, that could increase 10-fold, 100-fold, 1,000-fold before it's even remotely close to even another, you know, even close to the airline industry, which again is just so little. All of those are additive, you know, and unless you counteract your CO2 emissions through, you know, like a carbon tax or something like that, they're all going to be the same thing. So it's not like rockets are unique. And the cool thing, like I said, is some fuels can actually be carbon neutral. And airlines soon could be using renewable energy sources like that too. There's been talk of methane-powered airplanes. There's been talk of like algae growing, like, you know, I don't know, Joe Answers with Joe. He does a bunch of videos. You've talked about renewable energy. Oh, sorry. I called him out. Spotted. Paparazzi. But yeah, so, you know, that is something else that will help with airplanes. But in general, all of those things are additive. So anytime any industry makes a shift, we have to figure something out, because that's how all this stuff works. So yeah, good point. All right, that's it for me, guys. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut. Thank you guys so much for coming. I really appreciate it. And we'll see you out there.